Welcome to Lecture 3 of the online course on similarities and differences in natural language processing between humans and neural models. In the last two classes, we defined what language models are, and we saw how they can be implemented with a recurrent neural network. In this class, we will review another type of a neural architecture, convolutional neural networks, or CNNs in short, which can be used to implement a language model. The goals of this lecture are to highlight several computational properties of CNNs, utilize the computational properties of CNNs for natural language processing, construct neural language models with CNNs. Convolutional neural networks were originally inspired by the anatomy and function of the primate visual cortex. We will now remind several architectural and functional principles of the system, together with examples from the visual system. The first architectural principle is hierarchical processing, which means that information in the system is processed across many layers, such that each layer extracts increasingly abstract features by combining features from lower layers. For example, the visual system of the mammalian brain first extracts low-level features from an image, such as lines in different orientations. These are then combined in higher layers to extract more complex features such as contours, faces, and so on. Another computational principle is local processing. Each unit in the system receives input from only a small number of units in the previous processing stage. This means that its activation can be sensitive to only local patterns. For example, here we see that units process only a small part of the image. The kernel of its filter is limited to this region only. Similarly, the kernels of units in higher layers are limited to local regions of the previous processing stage. While the receptive field of units in earlier layers will be small due to the small size of their kernels, by stacking up many layers, the receptive fields of units in higher layers can be large and can even cover the entire image. Last, an important principle in CNNs is that they can develop translation invariance. Translation invariance means that the activations of units in deep layers can detect features regardless of where exactly they appeared in the input. For example, a unit in this layer will detect the digit 2 even if it's shifted to the right or left of the image. An important architectural property for translation invariance are pooling layers. For instance, the activation of a unit in a max pooling layer will be the maximal value in its receptive field. Small translations of the input will therefore not affect its activation. Since the system processes the input hierarchically across many layers with such local processing, this invariance to small shifts can accumulate across layers, leading to global translation invariance. These computational properties of CNNs can also be used for natural language processing. For example, imagine that we are interested in determining whether the sentiment of a given text is positive, negative, or neutral. Patterns, such as absolutely great, can be important features to identify a positive sentiment regardless of whether they appear at the beginning, middle, or end of the text. Translation invariance could be therefore useful also for representing and processing linguistic input. Such properties of CNNs can be achieved, just like in the case of vision problems, by stacking up several convolutional and pooling layers. For example, for text classification, by stacking up layers, a sequence of words can be processed and summarized by a single global vector. These global vectors can then be used for various tasks such as classifying text to different topics or sentiments. This can be done by simply adding a softmax layer at the top of the CNN, as illustrated in the figure, which can be jointly trained with the rest of the model. As we saw, units in CNNs receive input locally from a small set of units in the previous processing stage. This is shown in the figure here with small triangulars below the convolutional layer, which illustrate local receptive fields in the network. At each step, only a small number of words in the input is accessible. During training, the CNN learns multiple filters which could weigh such short word sequences in different ways, learning how to combine words in a hierarchical way in order to solve the task. However, when building language models, because the model is trained to predict the next word in a sequence, the kernels of units need to be limited to past words only. This ensures that the model does not have access to future words, which it is meant to predict. While the size of the kernel of each unit is typically relatively small, the receptive field of units in higher layers of the model can be large. The activation of such units can be sensitive to words that appear many time steps into the past. In this video, we saw another neural network architecture that can be used to implement and train a language model, convolutional neural networks, or CNNs in short. CNNs were inspired by several properties of the architecture and functioning of the visual cortex in mammals, such as hierarchical composition and local receptive fields. While originally created for visual processing, the properties of CNNs turned out to be useful also for language processing. For example, translation invariants can be beneficial for capturing a sentiment in the input, such as absolutely great, regardless of where exactly it appears. CNNs can be used for language modeling by limiting the kernels of the units to span across past tokens only. In this class, we examined a new type of neural architecture that can be used to implement and train a language model, convolutional neural networks, or CNNs in short. Join me in the next lecture where we will discuss attention mechanisms, transformers, and later state space models.